Hello again. Okay, let's continue our discussion on Venturi meter. I think this would be our second and perhaps the last example for Venturi meter. This could have been one of your experiments. Number five is a problem, an example on how to determine the coefficient of discharge of a certain Venturi meter. Okay, so since wala naman tayong Venturi meter na, meron tayong Venturi meter sa school, but I'll see if I can show you how we do that in the laboratory. But number five would somehow illustrate how we compute the coefficient of a Venturi meter, no, experimentally. So number five, in a test to determine the discharge coefficient of a 2 inches by 1/2 inches Venturi meter, the total weight of water passing through the meter in 5 minutes was 768 pounds. A mercury differential gauge connected to the inlet and throat of the meter showed an average mercury difference during the time of 1.18 feet. Determine the meter coefficient. So we have a Venturi meter. Okay. And then of course, we are tasked to solve for the meter coefficient given the following data. So what we need to solve for the coefficient of the Venturi meter C is the actual and the theoretical discharge. So we need to solve for the coefficient. We need the ratio of the actual and the theoretical discharges. Okay, so we can solve for the actual and the theoretical, I think. Yes, of course. Okay, first we need to solve for the theoretical discharge. Muna tayo. So how do you solve for the theoretical discharge? The same procedure sa previous problem na sinolve natin before. So we assign 2 points. We solve the discharge using the energy equation. We assign 2 points above the two legs of the differential manometer. We say this is point 1 and point 2. Apply the energy equation. So we have V1 squared all over 2G plus P1 over gamma plus Z1 equals V2 squared all over 2G plus P2 over gamma plus Z2. Since we are solving for the theoretical discharge, we are going to neglect the loss of energy from points 1 to 2. So, and the Venturi meter is laid horizontally, so the elevations of points 1 and 2 are the same. So that would cancel. We're left with the four terms here of velocity, in terms of velocity and pressure. Okay, again, let's try to manipulate the equation. All pressure heads at the left and then all velocity heads at the right of the equation. So we do that. So we have P1 over gamma minus P2 over gamma. That's equivalent to, we have V2 squared all over 2G minus V1 squared all over 2G. Again, we solve for the difference in pressure using manometry. So let's go to the differential manometer. Label points of equal pressures. So let's say this is point A and this is point B. The vertical distance between point 1 and A, let's assign that to be X na lang. So X. And then add pressure or pressure heads from 1 to 2. Let's start at point 1. We have P1. We go down to point A, so plus, since we're going down, and pressure increases with depth, so it's additive in nature. So we have X. By the way, this is this water? Water. So the unit weight of water is 62.4 pounds per cubic foot times the height, which is x, and then from point A we move upwards, so upwards and minus, minus, this is Mercury, I think this is Mercury, yep. So unit weight of Mercury, we simply multiply the specific gravity of Mercury by the unit weight of water times the height of Mercury, which is 1.18 feet. And then we move upwards again to point 2, that is minus, so this is already water is 62.4 pounds per cubic foot times the height of water, that is x minus 1.18, so x minus 1.18 feet, and that should be equal to the pressure at point 2. Okay, so this term would cancel ito, and we're left with the difference in pressure between the 2 points, which is, so P1 minus P2, we have 956.6496 pounds per square foot. The difference in pressure between points 1 and 2. We substitute this value in the energy equation, so we have 956.6496 pounds per square foot divided by the unit weight of water at 62.4 pounds per cubic foot. Okay, and should be equal to the difference in the velocity heads at points 2 and 1. So we have let's just solve this in terms of the discharge na lang. That would be long. Okay, let's just express the velocities in terms of discharge. So we know that the discharge at point 1 is also equal to the discharge at point 2. So let's just say Q na lang. Q. So, ayan, gawin natin. So, Q all over area. So we have Q, the theoretical discharge, divided by the area of flow at point 2, I should say. That should be point 2. It's pi. The diameter is, diameter ng point 2, that's 1/2 inch. I-convert natin sa feet. So 0.5 divided by 12, that is approximately equal to 0.0417 feet squared all over 4, square the entire term or quantity divided by 2g, that's 2.32 at 2.32 2g, 2 times 32.2 feet per second square. Okay, so this is the velocity head at point 2. This is the velocity at point 2, that's Q over area at point 2. Then minus, ito na lang, halay ko na lang sa baba, magkakasunod to. Minus, yeah, QT divided by pi times the diameter at point 1, that's 2 inches divided by 12, that is approximately equal to 0.1667 feet. Convert natin yung 2 inches sa feet, so we divide it by 12. So by 4 squared divided by 4 squared divided by 2g, that's 32.2 feet per second square. So we have only one missing or known in the equation, and that is the theoretical discharge. So the theoretical discharge, if you try to simplify and solve for the QT here, that should be equal to 0.043 cubic feet per second. That's a theoretical discharge. Okay, so we have solved the denominator dito. Next is to solve for the actual discharge. How do you solve for the actual discharge. Let me erase some parts of the solution na lang. So let's try to note the theoretical discharge 0.043 cubic feet per second. Next, solve for the theoretical actual discharge. Okay, so the actual discharge is equal to volume times divided by the time of collection. So habang in 5 minutes, so habang kinokollect natin yung amount ng tubig lumalabas sa outlet ng Venturi meter. Okay, so and then i-divide natin yung volume sa time of collection, which is 5 minutes, and that would be the actual discharge. Okay, so we need to solve for the volume, but the given value is the weight of the collected water. So how do you solve for the volume? Okay, we know that unit weight is equal to weight over volume. Okay, and volume is equal to weight over unit weight. So the given yung weight natin, unit weight of water is 62.4 pounds per cubic foot. So we can solve for the volume. The weight is 768 pounds. Unit weight of water at standard temperature pressure, that is 62.4 pounds per cubic foot. So pounds will cancel. We have a volume equal to 12.308 cubic feet. Now we can solve for the actual discharge. It is volume divided by the time of collection, that is 12.308 cubic feet divided by time, which is 5 minutes. I-convert natin into seconds to be consistent with the value of the theoretical discharge. So we have 5 minutes. How many seconds in 1 minute? 60 seconds in 1 minute. So cancel yan. So the actual discharge is 0.041 cubic feet per second. Now we can solve for the coefficient of the Venturi meter by simply solving for the ratio of the actual and the theoretical discharge. So 0.041 cubic feet per second divided by the theoretical discharge at 0.043 cubic feet per second. So we have a meter coefficient of 0.953. So this would be the coefficient of the Venturi meter. That's how you solve or determine the coefficient of Venturi meter experimentally. Okay? Yan. So dapat experiment sana natin to kung meron tayong face-to-face class. Okay. So I think we have one more topic under this chapter that would be discussed in a separate video na lang.